So nuclear transmutations where we break stuff apart are called nuclear fission. So you decay large elements into smaller ones. It can be a spontaneous decay, like you emit an alpha particle and you go down in mass, or it can be initiated by a collision with another particle. So on the left here, I have a picture of the chain reaction that you get from uranium-235 being hit by a neutron. So when you do that, it breaks up into barium and krypton, but plus 3 more neutrons. So you can see you're generating more neutrons than you are than you start with in the reaction. You can start to sustain this. Now that we've seen an example of nuclear chain reaction, we'll talk about nuclear decay chains. So here I have a graphic of the U-238 decay chain. Each of the boxes is labeled with the isotope and its half-life. U-238 decays by alpha emission into thorium-234 and has a half-life of 4.5 billion years. Thorium-234 decays with a half-life of 24.1 days into protactinium via beta emission. These decay chains can be quite long and will always end up with a stable element. This one ends with lead-206. Most high Z elements will decay into lead-206 because it's the largest stable isotope in existence. There can be more than one type of decay associated with a given isotope, which is not shown on this graph for simplicity. Why do decay chains matter? Well, they tell us how long the nuclear waste is going to be radioactive. So what are some of the causes of nuclear waste? Well, the production and deployment of nuclear bombs and the use of enriched isotopes, mostly uranium, for nuclear power generation. Nuclear chain reactions of U-235, previously shown, is why we use uranium for bombs and for power generation. So this brings us to the concept of fissile material. So when we can continue a reaction, a fission reaction, by making more of our initiator than we started with, we call that fissile material. So fissile materials are capable of self-sustaining nuclear chain reactions. In most nuclear reactors, this means you have uranium-235, plutonium-239, and plutonium-241, or some mix of the above. In the United States, we generally use uranium-235 because plutonium is considered something that you would use for a nuclear bomb. And so we have a bunch of nuclear treaties that cover that. France actually uses plutonium-239 and plutonium-241, but I digress. So all of these fissile materials have a critical mass. It's the amount of material needed to support a self-sustaining reaction. And that quantity, that critical mass, is dependent on the conditions of the system. So the pressure, the temperature, mostly it's the pressure and the temperature. As you increase the temperature, you decrease the amount that you need for a critical mass, which is how a nuclear bomb works. So the one that we dropped on Nagasaki and the one we dropped on Hiroshima work via this idea. So you start with a less than critical mass of material and you have a primary explosion and you create a higher energy and pressure environment, which then makes the uranium or the plutonium reach critical mass, and then you start that nuclear chain reaction and it's huge and you get a big explosion. Okay. Subcritical mass, that's the mass that you put up in the bomb to begin with, is less than the amount of material needed to support a self-sustaining reaction. And supercritical amount is the amount that is needed so that you get increasing rates of fission. So our nuclear bombs, back in the day, you would take a subcritical mass, put it with that explosive, the primary explosive, send it up, you would hit it with a lot of heat and energy from that primary explosion, which created the fact that you were at now critical mass. And then very rapidly, as that reaction took place, you reached supercritical mass, in which the rate of fission was increasing, because obviously as soon as you start having fission happen, it releases a lot of energy. Okay. Now, the flip side of this, and what we've been using it for mostly in the United States since then, is generating nuclear power. All right, so let's talk nuclear power plants. We enrich uranium to around 3.5 to 5% of U-235 in the mixture. It normally starts at 0.5 to 0.7%. And you can use diffusion using Graham's law. This is how we used to do it back in the day. Facilities a mile long in order to make that happen. Currently, we tend to use lasers, or we'd use centrifuges because they are both faster and less expensive than using diffusion. And in fact, we messed up Iran's nuclear power program by messing with their centrifuges, but I digress. So we create this enriched fuel, and we put it into pellets about, I think they're around 5 grams in mass. And you pile all those pellets together into rods. They're called fuel rods. You put them in a nuclear reactor. So the core has a bunch of pellets lined up. Around 75,000 tons, metric tons. Just a fairly large amount, but one pellet of nuclear material can generate as much as like a ton of coal. So you actually get a lot of power for very little mass. Okay, moving on. In order to keep the reaction from getting out of control, we have water, which is circulating, which is a moderator. So we control the temperature with the water. That's also how we're generating electricity, because when the water heats up, it makes steam. That steam is used to push a turbine, and that turbine is generating power. Anyway, and then we have control rods, which are neutron-absorbing materials, which we dip down in order to prevent the chain reaction from going supercritical. So we want to prevent a meltdown. If you don't put the control rods in, you get a supercritical mass at some point because it's going to heat up. You've got too many, the rate of reaction is increasing too much. And Chernobyl is a good example of a meltdown. You can look that one up if you want to. Anyway, most nuclear power has that reaction going on in the reactor, and then we've isolated the water that's close to the reactor from the water that we use to generate steam so that we don't have radioactive material going out into the world. Okay, so basically everything after the steam generation works like a normal power plant. You get the turbine running, that generates the power, we have water, we have to cool it all the way back down until it gets back to regular temperature in order to put it back into the body of water that it comes from. Just for the record, literally every nuclear reactor is located next to a large body of water because you can't do this process without a lot of water available or it would get out of control. In particular, Limerick is on the Schuylkill, FYI. The opposite of fission, things going from larger to smaller elements, is fusion. Nuclear fusion happens at high temperatures of around 1.5 million degrees Celsius in nature because it happens in the sun. And in those reactions, neutrons and protons can be forced together to make larger elements. So for example, we can take 2 protons, given here as hydrogen atoms, mash them together and make hydrogen 2 with 1 proton and 1 neutron, and then give off a positron plus lots of energy. You can take hydrogen 2 and combine it with another proton to get helium 3, plus the release of a lot of energy. You see the pattern. One of the great dreams that we have is using nuclear fusion, which does not have incredibly dangerous and long-lived nuclear chains, to generate power. Initiating this reaction on Earth requires temperature of around 100 million degrees. This generates a plasma, a phase of matter where gas has charge. Creating these little mini controlled suns costs a lot of energy, but it can also generate a lot of energy in a short period of time. There is a lot of money going into this research right now. And around $6 billion in investment targeted at companies working on this technology. So it's considered less of a long shot these days than it was in the past. The DOE is not the only source of funding for the technology. We do use fusion reactions for something practical currently, thermonuclear bombs. So our currently United States warheads are called thermonuclear bombs. There is a primary explosion in them, which initiates a nuclear fission chain reaction that rapidly raises the temperature and pressure within the warhead. That starts a fusion reaction. So nuclear fusion actually releases 4 times as much energy per gram as fission does. These bombs are often called hydrogen bombs because of the hydrogen combining into larger elements that is releasing the energy for the explosion. The output of these bombs is devastating. It's still radioactive because there's a nuclear fission chain reaction starting material, and this is the only positive part, greatly, it has never been deployed in a combat situation. But we have done test explosions underwater. You can look them up if you want to, if you're interested in that kind of thing. All right, let's go on to our summary. Fission splits larger nuclei into smaller ones. It happens along nuclear decay chains, which are long and usually end with lead-208 for the transuranium elements. It is used for nuclear power plants and for plutonium and uranium-based nuclear bombs. Nuclear chain reactions are required for both power generation and nuclear explosions. A subcritical mass is too low to sustain the reaction. A critical mass is just right, and a supercritical mass results in meltdowns and explosions. Fusion combines smaller particles and nuclei into larger elements. It is used for hydrogen bombs and theoretically for commercial power generation. It is less of an environmental disaster than fission.